All right, so
Let me give you a bit of a welcome and introduction. So it's my pleasure to introduce to you all Gillian Rusell from the Australian Catholic University, eventually, hopefully in person someday, and St. Andrews. And she will talk to us on how to prove Hume's law. So you've got 45 minutes to an hour, and then 45 minutes or so for discussion and questions. All yours.
all right, thanks, Sarah. Thanks for coming to listen, everyone. Greetings from North Carolina. So what I want to do with the talk today is tell you a little bit about the book that I've just written about barriers to entailment. And I'll tell you what that is in a minute. It is obviously a bad idea to try to give a talk by compressing everything from a book into one talk. So I'm not going to do that. What I'm going to do is focus on one particular problem for Hume's law and how to solve it, and hope that that gives you some of the flavor of what goes on in the book and is a bit of an introduction. Okay, so the title is How to Prove Hume's Law. In the book, okay, so first of all, let me see if I can move these slides. What is Hume's law? So Hume's law is the thesis that you can't get an ought from an is, or normative claims from descriptive claims using logic. So as a matter of logical consequence. That's kind of vague, it's kind of imprecise. So what I'm interested in is some personification of that idea. But it's called Hume's law because it's associated with this famous passage from Hume, where he seems to say in the treatise that something like this is the case. So I'll read this out. He says, "In every system of morality which I have hitherto met with, I've always remarked that the author proceeds for some time in the ordinary way of reasoning and establishes the being of a god or makes observations concerning human affairs. When of a sudden I'm surprised to find that instead of the usual copulations of propositions, is and is not, I meet with no proposition that is not connected with an ought or an ought not. This change is imperceptible, but is, however, of the last consequence. For as this ought or ought not expresses some new relation or affirmation, 'tis necessary that it should be observed and explained, and at the same time that a reason should be given for what seems altogether inconceivable, how this new relation can be a deduction from others, which are entirely different from it." Okay, so there is a substantial literature on whether Hume really endorses Hume's law, the idea that you can't get an ought from an is. That's not the literature that I want to engage with, because there seems to be this intuitive idea that has some life independently of Hume's endorsement, that you can't get normative claims from descriptive claims. And I'm interested in formulating this as one of several barriers to entailment that say you can't get sentences of some kind from premises of another. So here are some other examples. So these are other examples of barriers to entailment. You can't get universal claims from particular ones. That's something that you sometimes find in the logical atomists. Rusell says, no matter how many particular premises you have, a universal claim won't follow from that. You have to have a universal claim in your premises. There's the idea that you can't get claims about the future from claims about the past using logic alone. We might think of that as Hume's second law, since he's also famous for endorsing something like that. You can't get claims about how things must be from claims that only say how things are. That's a kind of modal barrier to entailment. And then in the philosophy of language, there are a lot of things said and some thought experiments that suggest that there is an indexical barrier to entailment. This is something like you can't get indexical sentences, or you can't get context sensitive sentences from premises that are not indexical or context sensitive. And then finally, there's the Hume's law case. You can't get an ought from an is. So I'm really interested in the project of trying to come up with a unified formulation of barriers like this. And in particular, in whether or not these barriers can be proved, for example, as meta theorems about appropriate logics. Hume's law really mostly unlike the others, is extremely controversial. So here are some people who have endorsed or defended in some form Hume's law. So we've got Hume, Popper, A.N. Pryor, Hare, Nell Smith, Anscombe, Shorter, Thompson and Thompson, Flew, Jackson, Jagger, Bunker-Scherer in German, Carmo, Pigden, Gerhard Schurz, Guevara, Singer, Brown, and Kit Fine. And then here are some people who have rejected Hume's law and argued that, in fact, it's false, at least in some form. So we've got Reinen, Foote, Anscombe, Pryor again, Black, Searle, Mavrodis, Kurtzman, Geach, McIntyre, Nelson, and Mateson. So spread out over a fairly long time, depending on what your perspective is. There's even been some sort of intra-philosopher controversy about Hume's law. Here's my favorite quote on this. It has often been said, in fact, I said it quite emphatically myself, that it's impossible to deduce ethical conclusions from non-ethical premises. This now seems to me to be a mistake. So when Hume's law gets talked about in logic or by logicians, it's often Pryor's work on the topic that they're engaging with. So there's this very famous example or counterexample to Hume's law that uses disjunction introduction and disjunctive syllogism. And that's kind of become central to the logical treatment of Hume's law. I actually want to deal with a different problem, a different counterexample to Hume's law today. And it shows up in various different places, but one place where it is written down and formulated fairly succinctly is by Mavrodis in Analysis in 1964. Here's his statement of the problem. So this is going to be a counterexample to Hume's law, which means it's supposed to be a valid argument with descriptive premises and a normative conclusion. Okay. So Mavrodis says, many ethical philosophers appear to accept the view that ought implies can. This view, which seems quite plausible, can perhaps be formulated more precisely as 1. Statements of the form N ought to do X entail the corresponding statements of the form N can or is able to do X. But 1 is equivalent to 2. Statements of the form N cannot or is unable to do X entail the corresponding statements of the form it is not the case that N ought to do X. And 2 appears to say that there is a non-normative statement which entails a normative one. Okay, if we avail ourselves of the language of modal and deontic logic, we can make this point even more succinct. So here's an instance of ought implies can. So if it ought to be the case that P, then it's possible that P, or it follows that it's possible that P. And then if that's valid, and we think contraposition preserves validity, we just contrapose, and that gives us, it's not possible that P entails it's not the case that it ought to be the case that P. And that second argument appears to have a non-normative or descriptive premise. At least it doesn't have any deontic operators in it like ought or permissible. But the conclusion of the argument is it's not the case that it ought to be the case that P, and that has a normative operator in it. And so maybe that's normative. And so we have a counterexample to Hume's law. So this is the problem for Hume's law that I'm going to be talking about. And just off the bat, there are a few things you might think that you could say about it. So here is sort of the logical space. Here are some options. So one thing you could say is that the left-hand side of the argument, the premise, is really normative after all, right? So maybe not possibly P is really a normative claim. That would take some work, right? It's not obviously normative, so that would be a project. But if we could say that not possibly P is really normative, then that would diffuse the counterexample. Second thought, we could say that the conclusion is not really normative. So this opens up the idea that maybe the negations of normative claims are not themselves normative, or that normative claims are not closed under negation. And one way you can sort of push that idea a little bit further is by thinking about some of the other barriers to entailment. So in particular, the idea that you can't get universal claims from particular claims. So you might ask whether the set of universal sentences is closed under negation. And it seems pretty obvious that it's not, that say for all x, f of x is universal, but the negation of that, not for all x, f of x, is equivalent to exists in x, not f of x. And that looks just like an existential statement. It's not a universal claim. So it's pretty plausible that the set of universal sentences is not closed under negation. Maybe the set of normative sentences is also not closed under negation. So that's some way you might want to go. Third thing you might say the argument isn't valid. I'm not going to push on that very much. The way certainly this talk is going to work, I'm thinking, let's suppose that the argument is valid and figure out, like, we'll give our opponent that and figure out what we can say about it. But one place in the literature where somebody would just say the argument isn't valid is in Pigden. He takes a fairly restrictive view about logic, where it's really just first order classical logic, that is logic for real. And so there's no deontic logic, and so we don't have to worry about complex deontic modal logics, and so we don't have to worry about this counterexample. But then finally, one way you might defend the barrier is by restricting it. You might say, okay, you can't get normative claims from descriptive claims except under certain very restricted circumstances, which you would then have to specify, right? So you would end up with a kind of limited barrier, no normative stuff from descriptive stuff, except if some condition is met. I think Schertz's solution you can see is falling into this kind of category. But of course, it raises the question, what are those restrictions going to look like? How do you make sure that they're not ad hoc responses to like this particular problem, which would sort of open the possibility that there might be other counterexamples you haven't thought of and hadn't responded to. Of course, if you could prove the claim that you're making, that would help rule out some counterexamples. In fact, by the end of the talk, I am going to be suggesting to you that option 4 is the right way to go. That is, we should restrict Hume's law in order to get a version that we can prove. And it will turn out that this argument is one of the special exceptions. But that's the end of the talk. And so we've got quite a bit of work to do before we get there. Okay. So what that work is going to look like, we are going to introduce a deontic modal logic in order to make things more concrete, in order to illustrate some ideas. I don't want to suggest that this is the one true deontic modal logic. What it really is the simplest deontic modal logic I could come up with that has all the features that I needed to have and has as few as possible, like other features that are distracting or confusing and sort of take us away from the main issues in some ways. So we'll introduce that logic and that will firm up the issues in some ways, but it won't solve the problem. Okay, let's just push on for now. Well, yeah, before we even get to that, there's like one thing that I think is worth an observation that's worth making. The deontic modal principles that we were just looking at. So I've called ought implies can DM1 here, and the contrapositive DM2. They are just two of a series of interrelated deontic modal principles that seem really likely to stand or fall together. So let me suggest some others. If we just take DM2 and we replace phi with not phi, and then we assume that ought is interdefinable with permissibility in the usual way, and diamond is interdefinable with the box in the usual way, then we can get this principle. So if necessarily phi entails is permissible that phi, and then contraposing that gives us this. There's a principle that's a little bit stronger than DM1, but seems like it could be motivated by the same kinds of things that motivate DM1, namely, if it's permissible that phi, then it's possible that phi. And if you do the same kinds of things to that, like you get these other principles. And one thing that's worth noting here is several of these are plausibly descriptive premises, normative conclusion, and they don't all involve negation. So if you look at DM3, we've got box phi entails it's permissible that phi, and DM7 necessarily phi entails it ought to be the case that phi. And that suggests that, that thing that I was saying about, well, what if the normative claims are not closed under negation? Whether or not that's true, it doesn't seem like it's going to solve this problem in its full generality, because here we have examples of descriptive sentences on the left, normative sentences on the right, but negation's not really floating around to cause the problem. Okay, so pushing on. Okay, so the way we're gonna set up this logic, well, we're gonna do it in a fairly hand-wavy way, but we're gonna describe a set of models and use that to characterize the entailment relation. So this DML model, it's a deontic model, will be a quadruple of W, which is a set of non-empty set of possible worlds. S is a subset of W. It also has to be non-empty. And you can think of that as the set of superb worlds. So it's S for superb, where everything is as it should be normatively. They're like normative heaven worlds. There's an actual world, which we'll use for defining truth in the model, and then an interpretation function, which assigns truth values to sentences relative to worlds. So here's a little illustration of one of these models. What we have here is a set W of worlds, there's just 5 worlds in there. And then some subset of W, has to be non-empty, is the set S of superb worlds. So in this diagram, I've just shaded a region gray to show you that W1 and W2 are the superb worlds in this model. One of the worlds has to be the actual world. So there's the actual world in the middle. I made it a square so you can see it's a little different. And then the interpretation function will tell us which atomic sentences are true at which possible worlds. Okay, so that's what the models look like. It's useful to think just about the 2 operators, or the 2 kinds of operators, deontic and modal, that we'll be thinking about most. So box phi will be true at some world, if and only if all the worlds in W are such that phi is true there. Right. So you'll notice there's no reference to an accessibility relation there. We're just assuming that, if you like, every world is accessible. So we're just quantifying over every world in W with box. That's one of the ways in which this model is very simple. And then we have these 2 deontic operators, permissible and ought. So permissible phi is true at a world, just in case there is some world in the set of superb worlds where phi is true. So if you like, if phi is true somewhere in normative heaven, then phi is permissible. And if phi is true throughout normative heaven, then it ought to be the case that phi. Right? So those are the truth conditions for the normative operators. Truth in the model is truth at the model's actual world. So looking at this model here, R is true in the model, and permissible Q is true in the model because Q is true at W2. And it ought to be the case that P is true in the model because P is true throughout the set of superb worlds. And then we get our entailment relation, gamma entails phi, if and only if every model that makes gamma true makes phi true. Okay, so with that logic, we can prove each one of the DML principles. So this is a logic in which those arguments are all valid. Okay, so I said that that will make the problem maybe a little bit more precise, give us a way of thinking about it, but it's not going to solve it. But part of my strategy for approaching Hume's law is to approach it in the context of the other barriers to entailment and to always ask, like, you know, what would we say about similar problems for the other barriers to entailment? And so we can ask if there are any similar problems for the other barriers to entailment. Like, is there anything like the argument ought implies can, or the contrapositive of that, that would be a problem for one of the other barriers? So I think there is. So here's the problem. You might think that the following is a plausible entailment. If something happens in the future, then it's possible. So if something happens in the future, then that thing is possible. Okay, so using a tense modal logic, we can write out that argument like this. And again, we find we've got a similar range of corollaries that you can get by kind of contraposing and interdefining. So G here is the tense logic operator that means that every time in the future phi is the case, and F is the tense operator that means that sometime in the future phi is the case. If at every time in the future phi is the case, then phi is possible. If it's not possible that phi entails that phi doesn't happen at any time in the future. If phi is necessary, then in the future phi will be the case. If it's not the case that in the future phi, then it's not the case that necessarily phi, and so on, right? So we also get a range of tense modal principles that talk about the interaction between tense operators and modal operators. And some of these seem to have claims on the left that are not about the future, but claims on the right that either have an F or a G in them, and so seem to be to some extent about the future. And the strongest of these, where there aren't any negations floating around to complicate things, would seem to be TM3 and TM7. So if necessarily phi, it follows that in the future phi, and if necessarily phi, it follows that at all times in the future phi. Okay, so that seems like a parallel problem to the what implies can problem for Hume's law, but this time for the thesis that you can't get claims about the future from claims that are about the past or the present. Okay, so it would be helpful to have a simple logic for thinking about tensor modality that has both tensor modal operators in it. And so we're going to introduce that. And what our tense modal logic models are going to look like is this. So we've got this 5-tuple of a set of possible worlds W that has to be non-empty, a set of times T. So sometimes when you do a tense logic, you also have a relation in there, the earlier than relation that orders those times, the same way you'd have a relation that orders the possible worlds and accessibility relation. T here is going to be a set of numbers, like the set of integers or the set of reals. And we will just assume the ordering relation that those numbers already have. So in this example of this little model below, there's like T1, T2, T3, T4. We're kind of assuming that T1 is in the past, and then going into the future, we get T1, T3, T4, right? All kinds of ways we could make that more complicated, but we're not looking at making it more complicated right now. Okay, so in addition to having this set of points, that's a set of possible worlds, and the numbers that are the times, so we'll have one of those points that's possible worlds picked out as the actual world. So this is this at, and then one of the times is the present moment, like the now. So we'll call that little n for now, and then an interpretation function. And the interpretation function is going to tell us for every pair of a world and a time, which atomic sentences are true at that world and time. So it's like atomic sentences get their truth values relative to time slices of possible worlds. So to figure out whether an atomic sentence is true, you need to know, which world we're talking about and what time in that world. So in simple cases, where there aren't too many times or too many worlds, you could think of the model as a little table like this, where we have the times in a column down the left here. And here we're sort of moving from the past at the bottom of the page to the future at the top of the page. And then the possible worlds in the row along the top there. So we've got W, we've got the actual world, and we've got U. So W and U are some other non-actual worlds. And then since atomic sentences get their truth values relative to a world and time, we could represent that just by filling it in the cell that's associated with that world and time. So if we want to say that P and Q are true at T1 and W, then in that cell for T1 and W, we just write P and Q. Okay. So this diagram with this little illustration of a model has a gray box in it, and nothing in the specification of the model corresponds to that gray box. That's in there to kind of make it easier to pick out an important part of the model, which is the cells for times later than the present time, later than the now, in the actual world. Right? So here's the now, and here's the actual world in the middle. So like actually now in this model, just P is true. But then as we go into the future in the actual world, we get P and Q, and then we get P and Q and R later on. So you can think of that gray box as like the actual future. Right? Okay. So little bit of like bookkeeping about the truth conditions for tense and modal operators, because there's a couple of decision points here that I just want to be clear about. So in the future, phi will be true at a time and a world if and only if there is some later time, sometime after that time, where phi is true in that world. Okay. That's as you would expect. But when it comes to the modal operators, you could have gone like two different ways. We could have made them kind of relative to time, so that what was possible was relative to time. But and this is something I didn't really talk about when I was talking about the principle that if something happens in the future, then it's possible. There really are like two different senses of possible that we use. And one of them is time sensitive. So I can say things like, you better take biology next semester so that it's possible for you to go to med school in 3 years' time, right? Where like what is possible seems to depend on like what's happened at different times. But then we also have this absolute sense of possible, where we say things like, there's no faster than light travel in the future because that isn't possible, right? So in that case, we seem to be quantifying over every time and world. Like if there's some possible world and time where something happens, then it's possible, right? So this is the interpretation of the diamond and the box that we need for getting the TML principles to come out right. So possibly phi will be true at some world time slice in this model, just in case phi is true in any cell of the model, right? So for example, at the actual world and the now, R, possibly R is true because there's some cell in the model where R is true. And then that makes box phi really, really strong, right? The only way to get box phi to come out true is to have phi be true at every cell in the model, every world and time, right? So in this model, with the little illustration, box P is true, but only because it's true in every cell of the model. Okay. So just as before, a sentence is true in the model if it's true at the world's, at the like actual now, the actual present of the model. And entailment is truth preservation over models. And that logic turns out to validate all the TM principles, meaning you can prove them by reasoning about these kinds of models. Okay, so we're going to take this tense modal logic and try to see how we might be able to formulate a barrier to entailment to prove about it. Right? And one thing that we're going to need is an idea of what it is for a sentence to be about the future or about the past, right? Which sentences are we going to classify as being the past sentences and which sentences are we going to classify as being future? You can see when we look at various counterexamples to the barriers, sometimes there's a question and we need a clear verdict on those things in order to be able to get proof. So here's an intuitive idea that's a bit vague that we're going to persistify over the next few slides, right? So here's the vague idea. Sentences are really about the future if their truth value is somehow sensitive to changes to the future, So changing the future can change the truth value of the sentence if it's really about the future. Okay, we're gonna think about different specifications of this by thinking about two different things you might mean by changing the future and two different things you might mean by sensitive to. Okay. Once we've done this, we'll look at like various consequences of picking different options. This bit is probably a little bit fast. So it's, there's a lot going on and it might be hard to like stay on top of all of it. There will be a slide at the end that will summarize like some of the observations that we've made. So just hang on to that slide and then you get the conclusions. Okay. So first up, two different things that we might have in mind by changing the future, right? First of all, you might just think, you see that stuff that's in the actual future gray box? You're allowed to mess with that, right? So change the truth values of atomic sentences for any time and world that is in the future of the actual world, right? So this little illustration shows you one way to do that. Instead of having P and Q true at T3 in the actual world, we could have Q and R true there. And then instead of having PQR true in the T4, we could just have none of the atomic sentences come out true there, right? Otherwise, the models are completely the same, right? So W is the same, T is the same actual world, same now. The only thing that's changed is the interpretation function, and that's only changed for the actual world and times later than the now, right? One thing that's a little odd about this, if you're thinking about sentences that could change their truth value in the model, if you change the model this way, well, it's true that in the future, P could change its truth value because that's true in the left-hand model, but not true in the right-hand model. But so could box P, right? Because box P is true in the left-hand model, but it's not true in the right-hand model because there's a time and world, namely T4 and at, where P is not true. So if that's what we mean by future switching, this unrestricted future switching, then ordinary modal claims like box P, they change their truth value when you change the future in that way. So that maybe is sort of overshooting a bit. Okay. So then that can make you think, well, what about if we restricted future switching, right? You're not allowed to do just any changes to the actual future. What you have to do is take some other possible future and switch it out with the actual future. So what's happened in this illustration is the models are exactly the same, except for the actual future here on the left-hand side has been switched over to be the future of U on the right-hand side. And then the future of U has been swapped in to be the actual future going forward, okay? When you do this, you can change the truth value of future sentences like in the future R, because in the future R is true in the left-hand model, but not true on the right-hand model. So that seems to be getting something right. But you can't change the truth value of necessarily P, because if necessarily P was true, it's true in all the cells of the model. And so switching out possible futures is not going to change that. You can only switch in the futures that were possible. Okay, so restricted future switching maybe seems to draw the line a little bit more finely. The other thing we were going to think about is what we meant by sensitive to changes in truth value. So here are two different possibilities. We might think that the sentence should be fragile with respect to future switching, either unrestricted or restricted, or we might think it should be breakable. So here's what I mean by these two different things, right? So that little curly V symbol, that's for future switching. So a sentence is future switch fragile, just in case whenever, so in any model where the sentence comes out true, there's at least one model, which is a future switch of that model, that makes it false, right? This is the stronger property, the one that's harder to have. So it's not just that sometimes if the sentence is true in a model, you can make it false by future switching. It's that every single model that makes the sentence true is such that some future switch will make the sentence false, right? one place where you can kind of see like why this is kind of where this is cutting is when you think about disjunctions. So in particular, if you think about a disjunction of a descriptive and a normative sentence, so maybe we've got P or ought Q, right? Oh, I guess we're doing future stuff, so P or future Q, right? So we know that future Q, we can like always make that false by changing a future, right? But P, that won't change its truth value if we just change the future. And so now we've got this question, the disjunction P or future Q. If that's true in some model, can you always make it false by changing the future? And the answer is no. Sometimes you can make it false by changing the future and sometimes you can't. So if it's true because P is true, but in the model, then future switching is not going to change that. And so the disjunction will remain true. But if P is false and future Q is true, you could make the disjunction false by changing the future. So it turns out the disjunctions of non-future sentences and future sentences, they're not future switch fragile. They are, on the other hand, future switch breakable, because future switch breakable is a less stringent property. So all it requires is that sometimes if the sentence is true in a model, you can make it false by future switching, right? That's true with the disjunction. And so disjunctions are future switch breakable. And so now we have this question, when we say that sentences are about the future, if they are sensitive to changes in the future, do we mean they're fragile with respect to future switching, or do we mean that they're just breakable? Okay. Actually, that sentence there is backwards. I keep meaning to change it. P or FQ is future switch breakable, but it's not future switch fragile. Okay. Here's one of the most important points about the difference between fragility and breakability. Fragility, being the more demanding property, makes it very easy to prove barriers, and breakability does not, right? Let me give you an illustration. So suppose we let sentences count as past if they don't change their truth values when we future switch, right? So something like in the past Q is going to remain true in a model, even if we change stuff in the future. That's not going to make any difference, right? And that's the property we'll use to characterize past sentences, right? So then we can prove that no satisfiable set of sentences that is past entails a sentence which is future switch fragile, right? The proof is pretty straightforward once you see it. So suppose you've got a set of sentences that's past and a conclusion that is future switch fragile. Then if there is a model of the premises, either that model is a model of the conclusion or it's not. If it's not, then you already have a counterexample. If it is, then just future switch until you find a model that makes phi false. And you know there has to be one because it's future switch fragile, right? And that new model will still make gamma true since gamma is past, meaning it's not sensitive to future switching. And so again, you have a counterexample to the argument, right? But this proof really depends on us saying there has to be one because the sentence is future switch fragile, right? It won't go through with future switch breakable in place of future switch fragile, since the crucial move, there must be one, doesn't hold. Okay, so here's the table that sums up the 4 possibilities we get by thinking about 2 different specifications of sensitive to changes in the future and 2 different specifications of changes in the future, right? So in this column, we have, suppose we mean unrestricted future switching and fragility. Well, then because fragility gives us proofs really easily, it will turn out we can prove a barrier. But it also has some weird consequences. So for example, box P ends up classified as future. And disjunctions and also related certain kinds of conditional end up classified as not future in a way that I think turns out to be fairly counterintuitive. One property that I haven't talked about yet is this dichotomy property. So when we do things with fragility, you end up with a set of sentences that are past. a set of sentences that are future, and a set of sentences that are neither. And so you have some sentences that you're not really talking about when you say things like you can't get sentences about the future from sentences that are only about the past. But when we use breakability, we can partition the set of sentences into like those that are about the future and those that are not. Right. Okay. So the option that has the nicest consequences for the taxonomy, I think, like figuring out what's future and what's past, is option D, right? So restricted future switching, in part because that says sensible things about box P. And it gives us dichotomy, which is nice. It says sensible things about the things that are sort of obviously about the future. But there's this one problem. There's a question mark in the proof cell. So it's not obvious that we can prove a barrier to entailment if those are the options that we take. Okay, so that is what these comments say on the slides. Okay, except then there's this thought, but if you're interested in proving a limited version of the barrier, maybe it's actually a positive that the proof hasn't just fallen out of picking breakability. Because if we want it to be a barrier that holds, except in some special cases, if we can prove it already before we've delimited the special cases, then that's too strong. Okay. One more kind of change of subject. So we can ask again, do we get any problems like this with any of the other barriers? So for example, at the moment, we've got box P gives us it's permissible that P, that looks like getting normative stuff from descriptive stuff. We've got box P gives us in the future P, that looks like getting future stuff from non-future stuff. I think that the following is also structurally a very similar argument. So everything is Q, therefore I am Q. Right, that wasn't meant to be a political example. I just picked Q as a predicate to get away from using P. This is supposed to be an argument in an indexical logic, something like Kaplan's logic of demonstratives. In the book, there's a simplified version of the logic of demonstratives to do it, but demonstrative logics tend to be really complicated, and so I'm not going to lay one out right now, but I'm going to talk more intuitively about the argument from everything has a certain property to I have that property, right? So, I mean, there's a reason people have thought there would be some kind of indexical barrier, and I think it's something like this. Indexical sentences are sentences whose truth value is breakable with context shifts, right? So, among the things that are contributed by the context are the speaker or the place in which the sentence is uttered. And if the sentence contains certain kinds of indexicals that are sensitive to that, so it's something like I am happy, then if we shift the context so that somebody else is the speaker, right, they might not be happy, right? We don't have to change who's happy, right? And now that sentence relative to that context of utterance is going to be false because we changed the context of utterance. Or if the sentence is, it is raining, right? And we change the place of the context of utterance, then we might go from somewhere where it's true that it's raining to somewhere where it's not true that it's raining. And even though we haven't changed the world, everything's still raining in all the usual places. The sentence goes from true to false with context shifting. Okay, so it seems plausible that indexical sentences are going to be breakable with context shifts, with changes of the context. And that gives you kind of an intuitive argument for why you would have a barrier to entailment for indexicals, right? So suppose we have an argument and there's a set of premises C, and they're all constant sentences, they don't contain indexicals. And there's a conclusion I, which is some kind of indexical conclusion, like I am happy. You would expect to be able to generate counterexamples by finding a model in which C is true and then varying the context until I goes false, right? So you would kind of expect there to be a barrier except there's one situation in which that won't work, right? If making C true has restricted the model so that no contexts are available that would make I false, for example, if all the context shifts of models that make C true make I true, then there won't be such a model that makes the indexical conclusion false while making the premises true, right? So that sort of limit on the intuitive indexical barrier suggests a formulation of a barrier theorem for indexical logic, right? So here's the formulation. If gamma is non-indexical and phi is indexical, then gamma does not entail phi unless every context shift of any model that makes gamma true also makes phi true. And it turns out that we can prove this. So suppose gamma is non-indexical, phi indexical, and also that the unless clause is not met. So that means there is a context shift of some model of gamma, call that n, that makes phi false. Then phi will be false, but gamma will be true because gamma is by assumption stable under context shifts, and m was a context shift of gamma, a model of gamma. So gamma doesn't entail phi. Okay, so with that limitation in the theorem, using breakability, like context shift breakability, we can prove the limited indexical barrier theorem. Okay, but this solution works in the tense modal logic case as well. So we can define a sentence as being future if and only if it is, meaning restricted now, future switch breakable, right? And then our theorem can say, if gamma is non-future and phi is future, gamma doesn't entail phi unless every future switch of any model that makes gamma true also makes phi true, right? So in the necessity case, if you've got box P, you've got a model which is such that every restricted future switch continues to make future P true. And so this meets the unless clause. Okay. So what happened to our potential counterexample? We had box P entails in the future P. Well, on these criterion, box P is future switch stable, and so it's passed. In the future P is future switch breakable, and so it's future. But any model of box P is such that all the future switches of that model make future P true. So the argument is valid, but it meets the theorem's unless clause. Okay, so the last thing we have to do is go back to Hume's law and try to make the same idea work, but with a deontic modal logic. Okay, so we need to specify an idea that I neglected to talk about at the beginning of the talk. You know, I said indexical sentences, they're the ones that are breakable with context shifting, right? And future sentences, they're the ones that are breakable with future switching. Right, what are normative sentences breakable with? Well, there's an idea that you find in Carmo and that Humberstone traces back to him. Normative sentences are breakable with changes in the normative standards. Okay, their specification of the idea is a little bit different, but we can ask ourselves, what does changing normative standards look like in our deontic modal models? Here's the answer. It looks like changing which non-empty subset of W is S. So which set of worlds count as superb. Okay, so call this S shifting since we're changing the set of superb worlds. Here is an illustration. So the model on the left is exactly the same as the model on the right, except for that gray box that represents the subset of W, which is the set of superb worlds. Okay. And so it's an S shift of the first model. And we will define a sentence as normative if and only if it is S shift breakable. All right. So we can think about, which sentences are going to be able to go from true to false if you shift which set of worlds counts as S. And we can look at which ones have changed their truth values between these two models. So in the left-hand model, it ought to be the case that P is true. But in the right-hand model, it's not, because W4 is now in the set of superb worlds and P is false there. Okay, and it's permissible that, let's see. I don't know, you could see that we could change permissibility claims, their truth values as well by S shifting. Can't see an example right now. Okay, here's a summary of some of the sentences that come out counting as normative. So it ought to be the case that P, it's permissible that P, the negations of ought claims. So it's not the case that it ought to be the case that P, that is the topic of some controversy in the literature. So that's how we end up legislating on that. But also disjunctions of the kind that Pryor's interested in and conditionals that mix apparently normative and non-normative claims. They count as normative in this case. Non-normative sentences include P, box P, diamond P, logical truths like it ought to be the case that P, or it's not the case that it ought to be the case that P, because they're logical truths, they're true in all models, and so no kind of model switching changes the truth value. Also unsatisfiable sentences, so contradictions, they come out as non-normative. And also, logical truths like if it ought to be the case that P, then it's permissible that P. That allows us to formulate deontic modal logic limited barrier theorem. So it says if gamma is non-normative, phi is normative, then gamma doesn't entail phi unless all models M of gamma, every model N such that N is an S shift of M is such that phi is true in that model N. Okay. And it turns out we can prove that just the same way as before. And so we might finish up by asking, what does that mean for the counterexample that this talk was about? The problem, the contrapositive of ought implies can, right? So there's the contrapositive of ought implies can. Turns out that not possibly P is not S shift breakable, right? Because if P is true at some world in the model, changing which world is superb won't change the truth value of that. So it counts as descriptive. And not ought P is S shift breakable, so it is normative. But the argument meets the theorem's unless clause. In models of not possibly P, there are no S shifts that can make not ought to be P false. Okay, and that is the end. Thank you very much.
Wow, that was great. I have all sorts of questions written down that I will first open the floor to other people who have questions. You can either use the raise hand functionality, or if you have trouble with that, you can just type Q in the chat and I will take things as they come. I see a hand from Greg.
This is really fun.
Pause the recording.